Okay, so we're back and we're at a brand new day, maybe. Who knows when you've decided to play this video, but we were talking about delocalization and we were focused on rule number 1. And rule number 1 said pi electrons move toward a carbocation or a positive charge. So here's an example. And this example says, number 1, does delocalization happen? Number 2, if it does, show the resonance forms. And number 3, if it does, show the resonance hybrid. Woo. Okay, my work's cut out for me here. Let's see what goes on. So here's a structure. I don't know what kind of structure it is, but it's a structure. And they put CH2 with a positive charge on it. And then that's an sp2 carbon right there. Okay, well, here, that's the sp2 carbon. Next door, that's my carbocation. And because they're neighbors, guess what's going to happen? Delocalization does take place. So, yes, the answer to A. Delocalization takes part because this pi electron, double bond, those electrons are going to move in. And when they do, they go closer to that positive charge. Well, I need to show that. So I'll draw this starting structure again. That's the easiest way, I think, for people to learn it. And the double bond is now going to move. So I'm going to erase this, and that carbon flip-flops it onto the other side. So that new double bond is going to go right there. When that does, well, the CH2 loses that positive charge because now it has extra. It's got those extra electrons that it needed. All right, so we'll erase that. But in doing so, this poor little old carbon that was involved in that double bond ain't got nothing going for it now. So guess what goes there? It's a positive charge. So there's my first form. But I don't need to stop here. I need to look at this molecule and go, can it move any other way? Right? What else can happen here? Well, let's take a look. Here in this example, we have another sp2 carbon, don't we? It's right there. There's the sp2 carbon involved in the double bond. And next door is a brand new carbocation that was given to it by the movement that happened beforehand. So I have another resonance form, and I need to show that one as well. So I'll start with my original. That's what I always do. It helps me kind of just see things clearly. And here was that positive charge. This is where we're starting. And folks, I need to show that this sp2 carbon, gets rid of that double bond, and it moves it to the other side. So it moves it there. In doing so, this little old carbocation has now disappeared. But this other carbon has just been shortchanged because a double bond has been ripped from it. But that's okay. That's where that carbocation ends up going. Folks, there's another resonance form. Now, I don't need to stop there because I need to question that one. And I need to say, listen, can any other movement happen? And the answer is yes. Yes, it can. So I have another resonance form that I can draw here. So what we'll do is we'll draw the original. The double bond was here, the double bond was there, the carbocation was here, and a double bond with a CH2 at the top. So here is the sp2 carbon. That is the sp2 electron, the pi electrons. And next door to that is a brand new carbocation that was just given to it. So this sp2 carbon is going to go, all right, I'll play the flip-flop game. So I'll shove my double bond here. And that way that takes care of the positive charge. And there we go. We'll erase it. And as you would expect, this poor little carbon that was right there doesn't have a double bond anymore. So therefore, this is now a positive charge yet again. Now, are we not done? Can this happen again? And the answer is yes, it can. So the reason is because there is a neighbor carbon, and that neighbor carbon is an sp2 carbon that has a double bond, and a double bond can flip all over once more. So here we have the ring structure. We have a double bond here, a double bond there. I'm just redrawing it. The carbocation was shifted there, and here it was a double bond to a CH2 group. Just like before, folks. Here we have an sp2 carbon that has a double bond. It's going to take one of those double bonds and it's going to flip-flop it to the other side, and it's going to go here. That in turn gets rid of that carbocation, and then what do we have left over? A carbon that has been shortchanged. And now we go all the way back up to here, and we can do it all over again. Folks, look at all of these different resonance forms. All of these different resonance forms. So if I needed to draw a resonance hybrid, well, here we go. There's the ring structure. Here was the CH2. This is kind of how we started, right? So a double bond here, a double bond there, a double bond here. I have just told you, look, carbocation, it doesn't stay there though, it moves. So it only stays there part of the time, and then part of the time it goes here, and then part of the time it goes down here, and then part of the time it goes up here, and then it goes back up to square one. In addition to that, look at what goes on. We have this double bond characteristic, but folks, that double bond characteristic doesn't stay there. It can actually move. And this one doesn't stay there. It can move. And this one doesn't stay there. It can move. So sometimes the double bond is here. And sometimes it can move up here, as what we saw in our first form that we did. Well, sometimes it's also down here because that was original, and sometimes it's here because that was original as well. But in our second version, look at what we did. We drew a double bond completely over to the right-hand side of the molecule. So sometimes the double bond can happen here. And then if we look at our next resonance form, look at where we moved that double bond. One showed up down here. So I can draw a dotted line there as well. And then in my last resonance form, look at where the double bonds are located. One was up here, and I can show that with a representation of a dashed line. Well, truth of the matter is, folks, this is a completely delocalized system and delocalized network. And if I went left-handed with this thing, what you will realize is that the carbocations could actually shift on these carbons as well. So here is the resonance hybrid for all of the resonance forms that begin to happen on this molecule. No one said this is pretty, and no one said that this was going to be easy, but it's going to be my job to make it as easy as possible for you. Now let's take a look at rule number 2. Rule number 2 says that pi electrons can move, and they can go to another pi bond. Okay, so that means I basically need to start looking at double bonds. Double bonds can move toward other double bonds. I mean, that's basically what that means. So let's take CH2, double bond, CH, and then on that, CH, and then on that, let's do a double bond CH2. Keep it simple. So all these carbons have 4 bonds. All of the hydrogens are suitable. Everything is happy. I mean, nothing crazy is going on to this molecule. And any old day, at any old time in the past, you would have looked at this and said, hey, it's a double bond. Double bond breaks. One group goes on to one group goes on to the other, and away we go. But now we have to start involving delocalization into our decision. I told you, it's a build-up process. It's foundational stuff, folks. No wonder a final is cumulative. How can it not be? So rule number 1 said dots, electrons, move toward a positive charge. Now, there's no positive charge here. Do you see one? I don't. I don't see a positive written on the molecule. Okay. So rule number 2 says pi electrons can move toward a pi bond. Oh, now this is probably meeting that rule number 2. Here is an sp2 carbon. It's involved in a double bond. Next door over is another sp2 carbon that's also involved in a double bond. That's a neighbor. Just like what we did with carbocations, it is a neighbor. That neighbor is a little close for comfort. They're really, really, really best friends. And they share almost everything together. Well, this carbon can make the decision to say, hey, listen, sometimes I'm going to have the double bond on the left, and sometimes I'm going to put the double bond on the right, because you're my neighbor and I feel like sharing, and I think that you can do that. So let's see how we represent this particular kind of delocalization. I'm going to just redraw the original. You know me. You know how I work. This is how I do it. And up here at the top, this carbon has pi electrons, and these pi electrons can be shifted over. Well, if that happens, the double bond gets erased from here, and the double bond would form here. Right? It flip-flops, just like they've always had in all of our other examples. It goes from one side of the carbon to the other. In doing so, though, this carbon says, oh, wait a minute. Now you're going to load 2 bonds on me to the left, and on the right-hand side, I've got 2 bonds there, and I've got this 1 bond from the hydrogen. I am overloaded, folks. This ain't going to work for me. I've got to fix myself. I've got to do something in order to make that work. Well, this carbon's going to look at its neighbor, and it's going to say, listen, I've watched your dog long enough. You're going to have to start taking care of it on your own at this point. You're going to have to take some responsibility. So it takes these electrons and it shoves them over. These electrons get shoved over to that particular carbon. So this carbon now has a full-blown negative, and this poor little carbon on the left-hand end, it was ripped of its double bond. It's shortchanged. So this is a positive carbon now. This is what delocalization does to that particular molecule. Folks, if this double bond moves inward, then this carbon's okay. It doesn't care about anything else. Right? It's only in it for his own or her own self-interest. And this carbon's not affected. Everything's A-okay with those. That's why it goes on. Those 2 carbons have an agreement together. And the agreement is, hey, you want to delocalize tonight? And they go, okay, yeah, sure. And then they get together, they delocalize, and they could care about anyone else that's around them. Who cares? It doesn't care what it does to this carbon. It doesn't care what it does to that carbon on that end. And in doing so, it gives this end carbon a full-blown positive. It gives this carbon a full-blown negative. And these 2 carbons, they're going to get fed up. They're going to go, oh, enough of spending time with, quote, your buddy. This is over. It's done. You are either going to settle with what you've got, or I'm going to take this negative and I'm going to push this back in, and you're going to take that double bond between you 2 at this point, and you're going to push that back to where it came from. Because look at what happens here. Rule number 1. Rule number 1 said sp2 carbon, and we have it, moves toward a neighbor positive charge. When that happens, a positive charge happens here, and folks, that negative and positive will be attracted to reform that double bond. If I wanted to do a resonance hybrid to show you what goes on here, I start with my original. CH2, double bond, CH, single bond, CH, double bond, CH2. Well, we know that the double bond doesn't stay put here, and we know it doesn't stay put there. So delocalization can happen here and here. Only part of the time is it there. But we also drew the double bond in between the two center carbons. So we know a double bond could exist at that point right there. Over on this side, this carbon does get a positive charge, but folks, it's only there for a little bit. That's it. So we can put a squiggle positive there. And then over to the right-hand side, this formed a negative, but it doesn't stay negative. So it will flip-flop back and forth again, depending on the mood that this molecule is in. So we put a squiggle minus there to let you know that sometimes it's negative and sometimes it's not. It's kind of like the old Almond Joy and Mounds commercial. Sometimes you feel like a nut and sometimes you don't, right? Well, that probably holds true to organic as well. You probably do feel a little nutty when you take this class, and sometimes I don't blame you. All right, so there's another example of electron pushing, delocalization, with pi electrons moving toward a pi bond. All right, so let's look at another. Let's do CH2 double bond CH to a carbon, triple bond to a nitrogen. Does electron movement happen? Yes or no? Does delocalization happen? Yes or no? Well, keep in mind, triple bonds are also sp2s. So they have a sigma bond and they have two pi orbitals. Those two separate pi orbitals overlap to give you the second bond and to give you the third bond. So that's fair game. It's fair game. Here we have an sp2 carbon. Next door, ding ding, there's another sp2 carbon. We've got some pi electrons there, folks. So I'm going to redraw the original. CH2, double bond, CH, single bond, carbon, triple bond, N. So this carbon could say, hey, I'm going to flip-flop. Because next door, we have an sp2 carbon. Next door, we have some pi electrons. So I'm going to take this bond here to the left, and I'm going to draw it, whoop, there to the right. Sorry, carbon, if you don't like that, you've just lost some negatives. I know that you're positive at this point, but I'm in it for myself. I'm in it to win it, and I don't care what you do. But right now, I'm focused only on me. And that carbon says, oh, I've got 3, now I have 2. No, this ain't going to work. What needs to happen is that one of these bonds need to go, and nitrogen, you need to take those electrons from that bond, so that way I can just have 4 bonds in total. And nitrogen's going to look at this and go, well, if I do this, then I'll do it temporarily, because that's going to make me negative, right? It's going to make me have a negative charge. Why? Why is that negative? Nitrogen has 5 valence. And when we assigned formal charges back in Module 1, well, we took 1 away from each bond, so 1, 2, and we took 1 away for each dot, 1, 2, 3, 4. So 5 minus 4, folks, this gives us a 1. 5 valence electrons, only 4 are represented, and we're shortchanging it 1. So that's why that's a negative charge. So this is a resonance form. And this will flip-flop back and forth, back and forth, back and forth, back and forth. So we need a hybrid drawn. So how do we do that? Well, I'll do CH2, double bond, CH, carbon, triple bond, N. So sometimes this double bond happens right here, right? So what I'll do is I'll show that with a dotted line. And sometimes that bond is flipped over on the other side of the carbon. So I'll do a dotted line there. I also see a movement of one of these lines as well. So I'll just erase that one and I'll show a dotted line there. So I know that something's going to be happening to the bonds in that area of the molecule. Well, this also squiggly positive, and this squiggly negative. This carbon never gets attacked. This carbon never changes. It just takes a bond from the left and it flips it over to the right-hand side. And this carbon never changes. It started off with 4 bonds. It ends up with 4 bonds. Even when delocalization happens, it's perfectly okay. Nothing goes on in that area of the molecule. But we do get movement. Electrons do move, and this is why. Pi electrons move toward other pi electrons. It treats it just like a positive charge. So in the next video, we're going to take a look at rule number 3. And rule number 3 says lone pairs can move toward a pi bond. Well, let's look at what some of these examples are going to show us, and we'll pick up from there next.